Welcome to this explainer. Today, we are going to decode the hidden technology that keeps us all miraculously connected. If you've ever wondered how your smartphone continues to function in the most impenetrable-looking buildings, you are absolutely in the right place.
Picture this. You step into a massive concrete elevator shaft, or maybe you're shoulder to shoulder with 50,000 screaming fans at a packed stadium. You pull out your phone, and somehow, miraculously, you still have 5 bars of service. Have you ever wondered how that is physically possible when thousands of other people are doing the exact same thing, surrounded by signal-blocking materials? To answer that question, we are going to walk through the dead zone problem, what DAS actually is, the 3 types of DAS architectures, the hardware and installation, and finally, preventing PIM interference. Let's kick things off with Section 1, the dead zone problem. We've all hit those frustrating dead zones, right? The reality is, standard local wireless access points and external cell towers have hard physical limits. Commercial buildings, underground facilities, and high-capacity venues like stadiums naturally block or overwhelm external RF signals. Think about it. Steel, concrete, and sheer human density demand a much more robust solution, simply because these environments require way more bandwidth than a standard setup can possibly provide.
That brings us to Section 2. What is DAS?
Enter our technological hero, DAS, or Distributed Antenna System. Simply put, it's an incredibly effective extension of a wireless network. It's designed to provide added coverage, capacity, or both within a specific geographic area or structure. It is basically the infrastructure that brings the network indoors, seamlessly blanketing the area with connectivity.
Here is how it actually works. A DAS is a network of spatially separated antenna nodes. These nodes are all connected to a common source via a transport medium. So, instead of one massive antenna doing all the heavy lifting, the system actively splits the transmitted power among several strategically placed antenna elements.
Think of it like watering your lawn. A single cell tower? That is like blasting a fire hose. It might reach far, but it's easily blocked by a tree or a wall, and the pressure is intense. A DAS is much more like a perfectly spaced sprinkler system. By splitting the power, it provides coverage over the exact same area as a single antenna, but with significantly reduced total power and vastly improved reliability. You can strategically locate these smaller antennas to eliminate dead zones in notoriously tricky areas, like elevator shafts, where steel and concrete usually completely block wireless services.
Moving right along to Section 3, 3 types of DAS.
So how do we build these highly efficient RF sprinkler systems? Well, engineers don't just use a one-size-fits-all approach. There are 3 primary architectures to choose from based on the size, footprint, and specific capacity needs of a building: passive DAS, active DAS, and hybrid DAS. Let's start with passive DAS. This architecture is simply an extension of an adjacent wireless network like your local carrier. It typically gets its RF signal from an off-air repeater or signal booster. The keyword here is passive, meaning there is zero active control of the RF signals beyond the initial amplification of that donor signal. Instead, a network of 50-ohm coaxial couplers and splitters acts as the transport medium to carry the RF signal throughout the building to the distributed antennas.
Active DAS takes things up a notch. While passive just distributes the initial signal, active DAS actually includes signal amplification directly at the remote units themselves. This active boosting is absolutely necessary when you're pushing signals through particularly dense structures where a passive signal would just fade away before reaching your phone. And then we have hybrid DAS, which, as the name implies, combines elements of both. It features multiple passive systems that are fed by a single passive DAS via fiber-fed remote units equipped with amplifiers. Basically, a hybrid DAS perfectly extends the footprint of a purely passive system, making it the go-to architecture for massive, large footprint applications. Think sprawling shopping complexes or international airports.
All right, let's get into Section 4. Hardware and installation.
None of these elegant architectural systems matter if the physical hardware isn't up to the task. The absolutely crucial point here is choosing the correct transport medium. We're talking highly specific coaxial cables, high flexible copper corrugated coax, super flexible copper corrugated coax, or high flexible aluminum coax. And to flawlessly link all these cables to the splitters and antennas, the industry standardizes on type-N connectors. But having the right cables is only half the battle. Installing them is a highly delicate operation. The engineers weaving these cables through a building's ceilings and risers must strictly follow 4 foundational physical rules. They must be extremely mindful of the pulling force, observe the maximum bend radius so they don't kink the inner core,
Maintain the cable's crush resistance, and constantly check the temperature ratings of the environment. If literally any of these four are violated, the physical integrity of the copper or aluminum is compromised and the signal degrades.
Which brings us to Section 5, preventing PIM interference.
Because even if you have the perfect architecture and flawlessly routed cables, there is an invisible enemy that can absolutely ruin your signal. We call this invisible gremlin passive intermodulation, or PIM. PIM is, essentially, self-generated RF noise. It happens when the transmit signals carried by the DAS interact with the nonlinear characteristics of the RF path components, the connectors, or even the surrounding environment. In a system designed to precisely control signals, this self-generated noise is a total disaster.
Surprisingly, this highly technical interference is most often caused by simple human errors during the installation process. We're talking about loose RF connectors, poorly prepared RF terminations, improperly mated and misaligned parts, or perhaps the most frustrating one, leaving tiny metal chips or shavings inside the connectors after cutting the cables.
Mitigating the negative effects of PIM requires an almost obsessive attention to detail during cable preparation and connector termination. Seriously, just one stray metal shaving left inside a Type-N connector can create enough noise to drastically lower the capacity of the entire antenna node, ruining the coverage for everyone nearby. So, the next time you effortlessly send a picture from the middle of a massive stadium crowd, take a second to look up. You just might spot the distributed antennas working silently above you, turning a fire hose of data into a perfectly tuned sprinkler system. Now that you understand the hidden nodes, specialized coaxial cables, and careful engineering required to banish dead zones and prevent PIM, it really begs the question, what other invisible infrastructures are secretly powering your digital life right under your nose?